all the real zeros. So notice how this problem says find all real zeros. It doesn't say find all rational zeros. So that means we might need to also find irrational zeros that are real. Just a reminder that rational doesn't mean rational or irrational has nothing to do with imaginary. Rational are numbers that can be written as fractions or whole numbers, and irrational are like decimals that don't repeat, don't terminate, whereas imaginaries are when we have a negative in a square root. So the imaginary or complex zeros is what we'll focus on in section 2.5. For now, though, we are going to deal with both rational and irrational. So let's look at our rational roots theorem. That means we're going to take factors of -8, right? Factors of -8 divided by factors of 1, because that's our starting coefficient here. So plus or minus, because it's always plus or minus. There's Ivy. Okay, we're using our new theorem called the rational roots theorem, which you can watch up on later. So we're taking the factors of our constant. So our constant is -8, and we're dividing it by the factors of our leading coefficient. So the leading coefficient is, we know what that is. And the constant is that number right there. So it's our factors of -8 divided by our factors of 1. Now, both positive and negative numbers are factors of those, and so we always have positive and negative possibilities. So that gives us, we just need all the factors of 8. So help me list out all possible factors of 8.
1, 2, 4, and 8, and they're all positive.
Positive or negative, yeah. It's because we could have a positive 8 and a -1, or a positive 2 and a -4, or whatever combination to get that -8. And then we have factors of 1, which would be positive or -1. But what happens when we divide by 1? We just get all the same numbers. It's not going to matter like it did in the last one. We ended up, the last example we did had a 3/2 in it and a 1/2 in it. This one is all going to be just those whole numbers. Okay, so what the rational roots theorem again tells us is it gives us the possible rational zeros of our polynomial function. That doesn't mean they are the zeros. It means they could be. It narrows down our possibilities from infinite to, in this case, 8. So now we can just do our synthetic division to try stuff. Just for fun, I usually start with 1 because it's easy. But just for fun, I'm going to start with 8. So here's my numbers. Make sure that there's no jumps in the degree of the term. So we've got 4th power, 3rd power, 2nd power, 1st power, no power. Bring down the 1. 1 times 8 is 8. -2 plus 8 is 6. 6 times 8 is 48. These numbers are getting really big. I don't think this is going to get to 0. That's our goal. I don't even want to keep multiplying this. It's so big. I am not going to get 0 at the end here, and that's all I care about. So I am bailing on this one. All right, let's go ahead and try 1. Probably starting with the biggest number was a bad idea. But it gave us an idea of how we can immediately tell that something's not going to work. So bring down the 1. 1 times 1 is 1. -2 and 1 is -1. -1 times 1 is -1. -7 and -1 is -8. -1 times 8 is -8. 16 minus 8 is 8. 8 times 1 is 8. And voila, we got a 0. Woohoo! So we have 1 0. I'm just going to start making a little list of zeros over here as we find them. Just for fun, just so I don't get them lost in my work somewhere. Now don't forget that it's possible to have repeated zeros. So just because 1 worked once doesn't mean it might not work again. I'm going to cheat a little bit for the sake of time, because at this point you could try 1 or -1. You can try all 8 possibilities again, now that we found one. So, although we wouldn't want to try 8, right? So looking back at my work from last year, look what worked a second time. 1 did, so I'm going to use 1 again. So that's just an important thing to remember when you're finding the zeros using the rational roots theorem and synthetic division, is sometimes you have repeated zeros, and so they divide in more than once. So you really, really, really want to check those by going from your previous answer, because obviously we know that 1 goes into our original problem. Our goal is to find out if 1 will now go into what we have left. So bring down our 1. 1 times 1 is 1. Negative 1 plus 1 is 0. 0 times 1 is 0. Negative 8 plus 0 is negative 8. Negative 8 times 1 is negative 8. And that brings our remainder to 0. So now we're left with a little quadratic here, x squared minus 8. So since we found out that 1 divides in twice, we have 2 zeros of 1, or in other words, we could say we have 1 with a multiplicity of 2. That means we have the factors x minus 1 squared, if you want to write it that way, times x minus 1, or x minus 1 squared, right? And then we also have x squared minus 8. Can we factor x squared minus 8? Well, only if we want to use irrational factors. If we want to use real factors, then no, because this would be like a difference of squares, but 8 is not a perfect square. So this would only work with integers if it was like 4 or 9 or 16. So 8 doesn't work, which is why we're going to have irrationals. So this one doesn't factor, right? So instead of factoring it, we're just going to take the whole thing, x squared minus 8. I think we saw something similar to this last time in class. X squared minus 8 equals 0. That means x squared equals 8. That means x equals plus or minus square root of 8. Because when we put a square root into the problem, we have to realize there's both a positive and negative possibility. And then we should simplify this. So I hope you guys are good at simplifying square roots. 8 would be 4 times 2. So the square root of 4 would be 2. And then left over inside would be square root of 2. So we have zeros 1, 2, positive, 1 twice, sorry, 1 and 1. And then positive 2 square root of 2, and then negative 2 square root of 2. Those are all of our real zeros. Now, the way the instructions are worded, it's saying they want us to find the zeros and their multiplicities. So in other words, that would mean that we would just say we have a 0 of 1 with a multiplicity of 2, and then our other real zeros are 2 square root of 2 and negative 2 square root of 2. Now, the reason these real zeros are not part of this list is because this list, this theorem, only gives us rational potential zeros, and these 2 zeros are not rational. So they cannot come from this theorem. Roots theorem.